Now, let us move to one of the most important ideas in mathematics, namely the composition of functions. In fact, composition of functions appear throughout calculus, differential equation, engineering, physics, economics, computer science, and especially machine learning. The basic idea is actually very simple. Instead of applying two functions separately, we use the output of one function as the input of another function. In other words, one function works first and then the second function works on the result. Mathematically, we write this operation as f of g of x equals f of g of x. We read this expression as f composed with g of x equals f of g of x. Notice carefully what happened here. The function g is applied first. Then its output becomes the input of the function f. This order is extremely important. Now let us study a simple example. Suppose f of x equals 2x plus 1 and g of x equals x squared. Our goal is to find f composed with g of x. As a result, the first step is to evaluate the inside function. Since the inside function is g, we begin with g of x equals x squared. Now we substitute g of x into the function f. Therefore, f of g of x equals 2x squared plus 1. Simplifying this expression gives 2x squared plus 1. So, f composed with g of x equals 2x squared plus 1. Anyway, now let us reverse the order of the functions. This time, we want to find g composed with f of x. Notice that this is completely different problem. Now, the function f is applied first. Since f of x equals 2x plus 1, we substitute this expression into the function g. Therefore, g of f of x equals 2x plus 1 squared. Therefore, g composed with f of x equals 4x squared plus 4x plus 1. Now let us compare our two answers. The first composition is 2x squared plus 1. The second composition is 4x squared plus 4x plus 1. Clearly, these two expressions are not the same. In general, f composed with g is not equal to g composed with f. In other words, the order of composition matters. This is very similar to many real-life situations. For example, suppose you first put on your socks and then your shoes. Everything works perfectly. However, if you first put on your shoes and then try to put on your socks, the result is completely different. The same idea applies to functions. Changing the order changes the result. Furthermore, composition of the functions plays a fundamental role in calculus. When we study derivatives, the famous chain rule is actually based on the composition of functions. Later, when we study inverse function, implicit differentiation, and many applications in engineering and machine learning, we will repeatedly use this concept. Now, let us study another important family of functions called piecewise functions. In fact, Many real-world situations cannot be described by single formula. Instead, different mathematical rules are needed for different interval of the independent variable. This type of function is called piecewise function because it is defined piece by piece. In other words, each part of the function has its own equation and its own interval of definition. Let us look at the example shown on this slide. We define the function as follows. F of x equals negative x plus 2 for x less than 0. And f of x equals x squared for x greater than or equal to 0. Notice carefully that this function has two different formulas. The first formula is used whenever x is less than 0. The second formula is used whenever x greater than or equal to 0. Therefore, before evaluating the function, we must first determine which interval contains the given value of x. Let us evaluate the function at a few points. First, suppose x equals negative 2. Since negative 2 is less than 0, we use the first formula. Therefore, f of negative 2 equals 2 plus 2, which is equals to 4. Now, let us find f of 2. Since 2 is greater than or equal to 0, we use the second formula. Therefore, f of 2 equals 2 squared, which is equal to 4. Now, let us consider for value of x equals 0. This point deserves special attention. Notice that 0 belongs to the second interval because the condition says x greater than or equal to 0. Therefore, we must use the quadratic formula. As a result, f of 0 equals 0 squared, which equals 0. Anyway, let us now examine the graph. On the left side of the graph, where x is less than 0, we see a straight line representing the equation y equals negative x plus 2. On the right side, where x is greater than or equal to 0, we see the right half of the parabola y equals x squared. Notice that the graph changes its rule exactly at the x equals 0. Furthermore, when studying piecewise functions, we should always pay close attention to the endpoints of each interval. A small symbol such as less than or equal to, greater than or equal to determines whether an endpoint belongs to one part of the function or another. Ignoring these symbols is one of the most common mistakes students make. In fact, a single incorrect inequality may completely change the value of the function at an endpoint. Piecewise functions appear frequently in science and engineering. For example, the price of electricity may change after a customer exceeds a certain level of consumption. Income tax is usually calculated using different tax brackets. Shipping cost often depends on different weight interval. Even traffic speed limit may change from one section of a road to another. All of these situations can be modeled naturally by piecewise functions. As we continue our study of calculus, we will encounter piecewise functions again when we study limits, continuity, derivatives, and optimization problems. Therefore, understanding this concept now will make many future topics much easier. Thank you for watching, and I look forward to seeing you in the next lesson of calculus.